NASA's Voyager 1 has been exploring a region beyond the Sun's protective bubble where the behavior of space is proving more complicated than our simplest models predicted. For decades, astronomers believed the boundary between our solar environment and interstellar space could be described as a relatively clear transition. But Voyager showed that nature is far less tidy. When scientists first examined the data, they found changes in charged particles, magnetic fields, and plasma that did not fit neatly into the picture they had expected. That detail matters. Voyager 1 did not suddenly appear there. It took decades to reach this frontier. Launched on September 5, 1977, the spacecraft was originally designed to study Jupiter and Saturn. Its cameras revealed details of those worlds that had never been seen up close, while its instruments measured magnetic fields, particles, radiation, and other properties of the outer solar system. After completing its planetary mission, Voyager simply kept going, and eventually it reached a place no human spacecraft had ever explored before. Today, NASA identifies Voyager 1 as the most distant human-made object, and the spacecraft crossed into interstellar space in August 2012. That sounds straightforward until you ask a much harder question. What exactly does interstellar space look like when you're actually there? The answer is not an empty black void. The sun continuously releases a stream of electrically charged particles called the solar wind. Over enormous distances, that outward flow creates a gigantic region of influence called the Heliosphere. You can think of it as a vast bubble surrounding the sun, although it is not a solid boundary and its shape is constantly changing. Beyond that bubble lies the interstellar medium, the extremely thin material between stars. The transition between these environments is called the Heliopause. Scientists had predicted that Voyager would eventually cross it, but predictions were based on observations from inside the solar system and mathematical models of conditions that no spacecraft had directly experienced before. That made Voyager something more than a distant probe. It became a measuring instrument at the edge of our own cosmic neighborhood. But there was a problem. One of Voyager 1's most useful plasma instruments had stopped operating decades earlier, after its planetary encounters. Plasma is simply gas made of electrically charged particles, and measuring its properties is one of the clearest ways to understand whether the spacecraft is surrounded mainly by material influenced by the sun or by the environment between stars. Without that instrument, the boundary was much harder to identify, so researchers had to listen for another clue. Voyager carried a plasma wave subsystem, an instrument capable of detecting waves moving through the extremely thin plasma around the spacecraft. It does not hear sound the way your ears do. Instead, it measures electrical oscillations in the plasma and translates those measurements into information scientists can analyze. And that instrument eventually detected something extraordinary. A powerful eruption from the sun in 2012 sent a disturbance racing outward through space. More than a year later, that disturbance reached Voyager 1. Voyager 1, the surrounding plasma began to oscillate, and Voyager detected the resulting waves. The frequency of those oscillations gave scientists a way to estimate how densely packed the plasma was around the spacecraft. The result was significant. The plasma was far denser than what Voyager had encountered in the outer regions of the Heliosphere, consistent with what researchers expected in interstellar space. When scientists went back through older measurements, they found earlier evidence that helped establish when Voyager had entered this new environment. The accepted date is August 25th, 2012. But reaching interstellar space did not mean Voyager had suddenly escaped every influence of the sun. That distinction is crucial. Even after crossing the Heliopause, Voyager continued to detect signs that the sun still mattered. The boundary between the heliosphere and interstellar space is not a wall. It is a complicated region where different flows of plasma, magnetic fields, and energetic particles interact. Imagine standing at the shoreline where two enormous bodies of water meet. You might be able to identify which direction each current came from, but the actual boundary would be full of waves, turbulence, mixing, and constantly shifting conditions. Space behaves in a surprisingly similar way. That is where the older models begin to struggle. Researchers had expected certain signatures when Voyager crossed the Heliopause. Some appeared exactly as anticipated. Energetic particles originating inside the heliosphere dropped dramatically, while galactic cosmic rays from outside became much more prominent. The pattern was unmistakable. Yet another expected change was much less obvious. Scientists had predicted that the direction of the magnetic field would change significantly as Voyager moved from the sun's magnetic environment into the interstellar magnetic field. Instead, the magnetic field strength changed while its direction changed by only a small amount. That was not the clean transition many models had suggested. It forced researchers to rethink what the heliopause actually looks like. For someone watching from Earth, this might seem like a technical detail. It is not. The structure of this boundary affects how particles travel through space, how cosmic radiation enters our solar system, and how the sun interacts with the material between stars. It also tells us something about our own cosmic protection. The heliosphere acts as a shield against some high-energy particles arriving from the galaxy. It does not block everything, but it changes the environment through which those particles travel before reaching the inner solar system. Understanding that shield means understanding its outer boundary. And Voyager is giving scientists the first direct measurements from the other side. There is another reason these measurements are so valuable. Voyager 1 is not flying through a perfectly calm interstellar environment. NASA observations have shown that the interstellar medium contains waves and turbulence on many scales. Some disturbances are generated by enormous events such as supernova explosions, while smaller waves can originate from activity on our own sun. Voyager can detect those waves because the plasma around it responds to them. In a sense, the spacecraft is sampling the texture of interstellar space. That is something our telescopes cannot simply photograph. A telescope can look across light years and reveal stars, galaxies, nebulae, and distant explosions. Voyager is doing something different. It is physically traveling through the environment it is measuring. That difference is enormous. For more than 4 decades of studying astronomy, one lesson repeatedly stands out. The most important discoveries often happen when nature refuses to match our simplest expectations. Voyager is a perfect example. The spacecraft was built in an era when personal computers were primitive by modern standards. Its mission controllers have had to manage aging hardware across billions of miles, while the spacecraft communicates with Earth through an incredibly weak radio signal. And yet the instruments that remain operational continue to return scientific information from a region no laboratory on Earth can reproduce at full scale. The data travel back at the speed of light, but even that is not instantaneous. Voyager is so distant that a radio signal takes many hours to cross the enormous gap between the spacecraft and Earth. Every measurement is precious. Every instrument reading represents a tiny piece of information gathered from an environment we cannot visit directly. And the farther Voyager travels, the more interesting the environment becomes. Scientists now know that crossing the Heliopause is not the same as leaving the sun's influence completely. The spacecraft is still moving through a region where solar effects can extend farther than simple diagrams suggest. The boundary itself appears more dynamic and structured than the clean, spherical shell often used in illustrations. That raises a deeper question. If the edge of our solar bubble is more complicated than expected, what does that tell us about the space between stars? The answer could affect how scientists model the heliosphere, how they understand the interstellar medium, and how they interpret the environment surrounding other stars. And Voyager 1 is giving us an opportunity that cannot be duplicated easily. Its instruments are not simply telling us that interstellar space exists. They are showing us that interstellar space has structure. It has density changes, it has waves, it has magnetic fields. It responds to events happening hundreds of millions of miles away. And at the boundary between the sun and the galaxy, these influences interact in ways that are still being studied. The mystery is not that Voyager found a place where physics stops working. Physics is still working. The mystery is that our simplified descriptions of this region are not always enough to capture what the spacecraft is actually measuring. That distinction is important. Science does not fail when an observation disagrees with a model. That is precisely when science becomes most useful. A model is a description of nature, not nature itself. When better measurements reveal something unexpected, researchers refine the model. Voyager has forced that process to happen at the very edge of our solar system. And the most revealing evidence may not come from a single dramatic measurement, but from the subtle relationship between plasma density, magnetic fields, and energetic particles as Voyager continues moving outward. That is where the deeper mystery begins. The most likely explanation is that Voyager 1 has entered a turbulent transition zone where the sun's influence and the interstellar environment interact rather than simply separating at a clean boundary. The evidence supports this because Voyager has observed changes in plasma density, energetic particles, and magnetic conditions that point to a region far more structured than the simple picture of a solar bubble surrounded by empty space. That distinction is important. The heliopause is not a physical wall. It is a changing boundary created by competing pressures. On one side, the solar wind pushes outward from the sun. On the other, the thin material between stars pushes inward. Where those influences meet, the result is a complicated environment shaped by motion, magnetic fields, and waves traveling through plasma. And Voyager is directly inside that environment. To understand the scale, picture the sun not as a bright point surrounded by nothing, but as the center of an enormous moving system. The solar wind has traveled billions of miles before reaching the region Voyager is exploring. The spacecraft itself is now more than 160 astronomical units from the sun, meaning more than 160 times the average distance between Earth and the sun. Light and radio signals still need many hours to cross that enormous gap. Pause on that distance. Voyager is not merely observing the edge of our neighborhood from Earth. It is physically out there, sampling an environment that takes hours for its measurements to reach us. That makes every surviving instrument extraordinarily valuable. One of the most important clues comes from Voyager's plasma wave subsystem. Although the spacecraft's original plasma instrument is no longer operating, the plasma wave detector can still sense electrical oscillations traveling through the thin material surrounding Voyager. Those waves are useful because their frequency depends on the density of the plasma. In simple terms, the more particles packed into the plasma, the higher the characteristic frequency of certain plasma waves. By detecting those oscillations, researchers can estimate conditions around the spacecraft without directly collecting the particles themselves. It is an elegant solution to an aging spacecraft problem, and it has produced a remarkable scientific record. After Voyager entered interstellar space, researchers detected plasma waves that indicated the density around the spacecraft was substantially greater than the density typical of the solar wind far inside the Heliosphere. That difference helped confirm that Voyager had crossed into the interstellar medium. But the measurements also revealed something more subtle. The interstellar environment is not perfectly smooth. It contains waves, it contains variations, and it responds to disturbances moving outward from the Sun. This means the space beyond the Heliopause is not an isolated realm where the Sun suddenly becomes irrelevant. Solar activity can still send disturbances outward, and when those disturbances encounter the surrounding plasma, they can produce waves that Voyager detects long after the original solar event occurred. That connection is scientifically fascinating. When researchers examine data like this, they are not simply asking, "Where is Voyager?" They're asking what the spacecraft can tell us about the environment surrounding the entire solar system. The answer could improve our understanding of how stars interact with the space between them. Consider what that means. Every star in the Milky Way produces some kind of environment around itself. Some stars have powerful stellar winds. Others are surrounded by dense clouds of gas and dust. The boundary between a star's influence and interstellar space can therefore look very different from one system to another. Our Sun gives us the only nearby example we can study directly. Voyager is providing the measurements. That is why an aging spacecraft launched in 1977 can still matter to modern astrophysics. Its technology is old, but the environment it is measuring cannot be recreated simply by building a more powerful computer on Earth. If you enjoy exploring discoveries like this through clear, evidence-based science, consider subscribing so we can continue examining the universe together. The real scientific value of Voyager is not that it found a place where physics stops working. It found something more useful, a natural laboratory where our models can be tested against direct measurements. And models matter. Scientists use mathematical models because space is too large and too complex to observe everywhere. A model allows researchers to predict how the heliosphere should behave under different conditions. Then spacecraft observations provide a reality check. Sometimes the model works beautifully. Sometimes nature adds another layer. The magnetic field is a good example. Inside the heliosphere, the Sun's magnetic field is carried outward by the solar wind. Beyond the Heliopause, Voyager encounters the interstellar magnetic environment. Scientists expected a meaningful transition between these two regions, but the actual magnetic field behavior is more complicated than a simple diagram might suggest. Voyager measured a magnetic field whose direction did not suddenly swing into a dramatically different orientation at the boundary. That observation became an important clue. One interpretation is that the heliopause and the surrounding interstellar magnetic field are interacting in a way that creates a smoother or more complicated transition than early models assumed. Another possibility involves the structure of the heliopause itself and how plasma moves along and around that boundary. The evidence does not yet reduce the entire region to one simple explanation, and that is exactly why researchers keep studying it. In more than 25 years of following deep space discoveries, one pattern becomes impossible to miss. Major scientific progress rarely comes from one spectacular measurement. It comes from several independent observations, gradually pointing toward the same physical picture. Voyager offers that kind of evidence. Energetic particles provide one clue. Plasma waves provide another. Magnetic field measurements add another. Together, they create a much richer description of the environment than any single instrument could provide. One measurement alone is limited. The pattern is much stronger. Energetic particles are particularly important here. Inside the heliosphere, the solar wind and magnetic fields influence the movement of high-energy particles. Some energetic particles generated within our solar system become much less abundant as Voyager moves beyond the heliopause, while galactic cosmic rays become more prominent. Galactic cosmic rays are extremely energetic particles traveling through the galaxy, often accelerated by violent astrophysical events such as supernova remnants. The change in those particle populations is one of the strongest indicators that Voyager entered a fundamentally different environment. But there's a deeper question. How does the heliosphere protect the planets inside it? The answer is not that the heliosphere forms an impenetrable shield. It does not. High-energy cosmic rays can enter the solar system, but the heliosphere modifies the paths and energies of many charged particles before they reach the inner solar system. That makes its outer boundary scientifically important for understanding the radiation environment around our sun. It may also matter when we study other stars. Astronomers can observe stellar systems thousands of light years away, but they cannot send a spacecraft to their boundaries. They have to infer what those environments might look like from indirect observations. Voyager gives us a reference point. If scientists can understand how our sun creates and maintains its heliosphere, they can use that knowledge to build better models of stellar environments elsewhere. This is where the story becomes much larger than one spacecraft. Voyager 1 is helping us understand what happens when a star meets the galaxy. The spacecraft is also teaching us something about the limits of prediction. Earlier models were not useless because they failed to capture every detail. They were necessary starting points. The new measurements simply reveal where those models need more complexity. That is how science advances. A theory is not weakened because nature is complicated. It becomes stronger when researchers identify exactly where it needs refinement. The same principle applies to the strange behavior Voyager has encountered beyond the Heliopause. There is no evidence that physics has broken down. There is evidence that our simplified picture of the solar system's outer boundary was incomplete. That may sound less dramatic, but scientifically, it is far more interesting. Because if the boundary contains unexpected structure, then the next question is what creates that structure? Is it turbulence generated where solar and interstellar plasma interact? Is the magnetic field shaping the movement of particles in ways that earlier models underestimated? Are waves traveling through the interstellar medium carrying information from distant solar activity? Or are several of these processes operating together? Researchers are still investigating, and Voyager continues to move outward. Every mile carries it farther from the sun and deeper into an environment humanity has only recently begun to sample directly. Its power is declining, and its instruments will not operate forever. Eventually, the spacecraft will become silent, but the scientific record will remain. Future missions designed specifically to study the outer heliosphere could provide measurements Voyager was never equipped to make. Improved plasma detectors, more sensitive magnetic sensors, and instruments built with modern technology could examine this boundary in far greater detail. Those missions could test whether the patterns Voyager observed are unique to our solar system or common around other stars. That is the larger significance. Voyager did not discover a violation of physics. It discovered a frontier where physics becomes difficult to simplify. And that is precisely where exploration has always been most valuable. More than 4 decades after launch, a spacecraft built to explore Jupiter and Saturn is still helping us understand where the sun ends, where interstellar space begins, and how those two environments actually interact. The universe did not become stranger because Voyager traveled farther. We simply became capable of measuring the strangeness that was already there. And as future spacecraft carry better instruments into that distant frontier, the quiet measurements from Voyager 1 may become the foundation for an even clearer understanding of what truly lies beyond the solar system.